And in this video, we're going to do section 4.2. We're going to talk a little bit about exponents. I'm going to start off by defining and kind of explaining the notation of an exponent. Let me get my pencil ready here for you. Okay, so if we're talking about an exponent, we're talking about repeated multiplication. So I'm going to go ahead and write that up here for you. It's going to be repeated multiplication. And then I'm going to also talk about a different terms in the notation of it. So if we're talking about something in exponential form, I'll write that up here, exponential form. What we're doing is we're taking some number, and notice here I'm going to work with letters first, but we're going to take some number A. This is going to be called our base. And we're going to raise that base to an exponent. So here I'm just going to use the letter M for now. So this is our exponent. And what this is doing is it's telling us that we want to take A times itself M number of times. So for example, if I'm looking at 2 to the third power, this is going to take our base of 2 multiplied by itself 3 times. The common mistake here is that people want to say that that is fixed because they see 2 times 3, but it's not. Because keep in mind, it's 2 times 2, which is 4, times 2, which is 8. So do not multiply the base by the exponent. If you're confused, just go ahead and write it out. It's always better to show more work than less. Notice how I wrote that notation, or how I read that notation. It was 2 to the third power. I'm going to clear this and stay on this slide. I have a couple things I want to talk about on that note. So there are different ways that we can read these. We could have some number. I'm going to use 2 here as a base just for consistency, but we can have some number to the 0 power. So this would be 2 to the 0, or 0th power. I know that sounds weird. We then can keep going. This would be 2 to the first. And then something interesting happens whenever we're getting to exponents of 2 or 3. So if I have 2 to the second, we can also consider that to be 2 squared. And the way to think of that is if we have an exponent of 2, think of it like 2-dimensional, like a square. If we have 2 to the third, now we're thinking of 3-dimensional. So notice what I drew here was a cube. So we would say 2 cubed. Anything after that, we're just going to say the base raised to the exponent power. So this would be 2 to the fourth and so on. A quick note about anything to the 0th power. Remember that exponents are going to take that base times itself, however many times that exponent's there. So 2 to the first is 2, 2 squared is 2 times 2, 2 to the third or 2 cubed would be 2 times 2 times 2, and so on. Notice if we're looking at 2 to the 0th power, we don't actually have the base, because if I write the base, now I'm at 2 to the first. So anything to the 0th power is just going to give us the number or the value of 1. It doesn't matter what our base is. Go ahead and move on to some properties of exponents. Okay, so if we're talking about properties of exponents, a couple different scenarios could happen. So we could have 2 values that have the same base. So for example here, if I'm looking at x to the 6th times x to the 7th, Notice that our bases are the same, so they both have a base of x. And if we're looking for the product of powers, so we're multiplying them, what we want to do is we want to keep that base and add the exponents. So if we're multiplying here, we're going to keep that base of x and then add those exponents. We're going to have 6 plus 7 as our exponent. In other words, this is x to the 13th. I'm going to do another example there before moving on to quotient. Let's say that I have, so this is still with product. Let's say that I have 2 to the 3rd times 2 to the x power, and we set that equal to 2 to the 9th. If we needed to determine what the power or what the value of x is here, we need to remember the rule. So we're going to keep that base and add the exponents. So we know that this would be 2 to the 3 plus x is equal to 2 to the 9th. And now since they have the same base, we can set our exponents equal to each other. So I'm going to take this 3 plus x and set it equal to 9. So then we can determine that our value of x here is going to be 6. And I can double check that over here as well, right? So this was 2 to the 3rd. We're saying that x is 6. And we want to know, does that equal 2 to the 9th? Well, keeping our base and adding our exponents, we can see that we do get 2 to the 9th there. So our value of x is 6. I'm going to erase this and move on to quotient of powers. Remember here that if we're talking about the quotient, we're looking at dividing. So if I had a problem such as x to the 3rd over x squared. So we want to keep the base and subtract the exponents. We're going to keep that same base of x and subtract top minus bottom of our exponent. So 3 minus 2, that gives us x to the 1st. And we don't have to keep that 1 there. If we don't see anything, so x is actually the same as x to the 1st. So either one of those is okay with me. Let's look at another example. Let's look at 8 to the 5th over 8. If we want to write this as one value, we can simplify here. So we're going to keep that base. Remember, we don't see it down here, but this 8 has a power of 1. So it'd be 8 to the 5 minus 1, or 8 to the 4th power. Some of these values are going to be a little bit larger. So unless I tell you to evaluate, it's okay to just write it as the base with its exponent. I want to do one more example here. What if I gave you a problem, or what if we had a problem like 2 to the x over 2 to the 3rd? So again, here you can probably figure we're going to determine the value of x. We have this equal to 8. Well, we know on the left side, we're going to keep that base and subtract the bottom from the top as far as exponents. And now it seems a little difficult, right? Because it's like, where do I go from here? It's important to remember how this 8 came to be. So I'm going to rewrite this left side. I know to get 8, I can take 2 times 2 times 2. In other words, I can take 2 cubed. Now notice on each side of the equation, we have the same base. So we can do the same thing we did before and set our exponents equal to each other to solve for x. So adding 3 to both sides, oddly enough here, we have x equal to 6 again. And I'm going to double check that. So if I go over to our original problem, it would be 2 to the 6th over 2 to the 3rd. And we're wondering if that's equal to 2 to the 3rd. So on the left side, we're going to take 6 minus 3. We have 2 to the 3rd equal to 2 to the 3rd, and we are good. Let's move along to problems that we can encounter if we have different bases. So now let's look at something. If we have different bases, we're just going to look at power here. So power of a product. So we're multiplying and then raising it to a power. Let's look at an example such as 2 times 5 to the third. So notice we're taking the power of a product. Whenever we're looking at power of a product, we have different bases. We want to find the power of each factor and multiply. So what we're doing here is we're going to take each factor raised to that power. This one seems like it would be complicated to solve, right? We have 2 to the third times 5 to the third. But keep in mind that this is 2 times 2 times 2 times 5 times 5 times 5. Doesn't seem to simplify it right off the bat, but remember in the last section when we're talking about mental math, we can rearrange our factors to make the multiplication a little bit easier. So I'm going to regroup here, and I'm going to make this 2 times 5 times 2 times 5 times 2 times 5. And now we can see we have 10 times 10 times 10, or a value of 1,000. Another way we can approach that, and we're looking at the same problem here, is we could multiply what's in the parentheses first. So 2 times 5 is going to give us 10. And then we have 10 to the third power. So notice we've just jumped a couple steps by doing what was in the parentheses first. And we'll talk about that a little bit more in the next section as well. So 10 times 10 times 10, we saw we still get that same value of 1,000. Maybe one more example here for you. Let's say that we have a problem such as this: 2 to the fourth times 6 to the fourth times 5 to the fourth. Well, again, what we can do is, since we have different bases, let's go ahead and just multiply that 2 times 6 times 5 and raise that whole thing to the fourth. Just like in that last one, we saw that we could go one direction with it or the other. So now I'm going to, again, mental math. 2 times 5 is 10, times 6 is 60 to the fourth. I'm not going to have you multiply this one out. So purposes of making the problem easier, 60 to the fourth is okay with me. We have one other property we want to make sure that we're aware of, and that's power of a power. So it sounds complicated at first, but we're taking something raised to some power raised to another power. So for example, if I have 2 squared cubed, so I'm taking that whole value and then I'm going to cube it. What we want to do is we want to multiply the exponents. So notice we're taking the power of a power here. We're going to multiply those exponents. So 2 times 3 gives us 6, and we would have 2 to the 6. We can also kind of combine what we saw before with this one as well. So properties can overlap in one problem. Let's say that I was looking at an example like 4 times x times y to the third. So I'm going to take 4 to the third, x to the third, and y to the third. So it looks very similar to what we were doing before, power of a product. But imagine that each of these pieces has a 1 there. And we're doing that same thing. We're multiplying the exponents as we go along. So 4 to the 1 times 3, so that's the third power. And the same for that x and that y. Here, this one's not too bad to simplify at all. So this can just go ahead and become 64. Again, that's 4 times 4 times 4. Then we have x cubed, y cubed. In the next section, we're going to move on to order of operations. And we're going to talk about kind of combining our exponent rules into different expressions and how we can simplify something that looks really complex at first into just a single expression.